For decades, archaeologists believed they knew when humans first learned to weaponize nature's chemistry. The textbooks pointed to ancient Egypt, bone arrowheads from a tomb along the Nile coated in toxic residue dating back roughly 4,000 years. That was the starting line. That was when our ancestors supposedly crossed the threshold from simple projectiles to something more sophisticated, something deliberate, something designed not just to wound, but to weaken. Then a set of quartz arrowheads from a South African rock shelter upended the entire timeline. The artifacts came from Umlatuzana rock shelter in KwaZulu-Natal, a site tucked into the rolling hills of eastern South Africa. Road construction crews unearthed the site in 1985. Archaeologists salvaged what they could from the exposed sediment layers, thousands of stone tools, animal bones, the debris of lives lived 60,000 years ago. Among them, 10 tiny quartz points, each no larger than a thumbnail, their edges still sharp after millennia in the ground. For nearly 40 years, these microliths sat in storage at the KwaZulu-Natal Museum. Researchers had examined them, noted their shape and fracture patterns, cataloged them alongside countless other Stone Age artifacts. What no one had done was ask the right question. What no one had thought to look for was what might still be clinging to their surfaces. That question finally arrived in 2005. The old consensus on poison weapons had seemed solid. Egyptian arrowheads from Naga Ed Dere provided the benchmark, around 4,000 years old, coated in a black toxic residue. Later discoveries pushed the date back modestly. Bone arrow points from Kruger Cave in South Africa carried cardiac glycosides dated to roughly 6,700 years before present. At Border Cave, also in KwaZulu-Natal, researchers found a wooden stick interpreted as a poison applicator, alongside a lump of beeswax that might have served as adhesive, both dating to between 24,000 to 35,000 years ago. But these were indirect clues. The Border Cave finds suggested poison use. They didn't prove it. The applicator could have served other purposes. The beeswax might have had nothing to do with hunting at all. What archaeologists lacked was direct evidence. Toxic compounds detected on the weapons themselves, chemically verified, sourced to specific plants. Without that, the true origins of this technology remained speculation. 3 factors had masked the deeper history. First, organic molecules break down. Most plant-based poisons are unstable. They dissolve in water, degrade in soil, vanish within centuries or even decades. The chance that any residue would survive 60,000 years seemed negligible. Researchers weren't looking because they assumed there would be nothing to find. Second, the focus had been on bone arrowheads. Stone microliths, the tiny quartz blades used as composite arrow tips, received less attention for residue analysis. Their mineral surfaces seemed unlikely candidates for preserving organic trace. Third, the sedimentary conditions at most sites weren't conducive to preservation. Moisture, acidity, microbial activity all conspire to erase the chemical signatures of ancient organic compounds. Only under specific conditions, in specific soil chemistries, might such traces survive. Umlatuzana turned out to be one of those rare exceptions. Geoarchaeological studies conducted in the early 2020s revealed something unexpected about the site's stratigraphy. Certain sedimentary layers, particularly the red-brown sand deposits excavated in 1985, had experienced less moisture exposure than others. The conditions, it turned out, were conducive to organic preservation. The same researchers who had studied use-wear patterns on the quartz microliths, who had identified fracture signatures consistent with projectile impact, who had documented residue traces suggesting complex adhesives, realized there might be something more to find. Sven Isaksson, a professor of archaeological science at Stockholm University and an expert in ancient organic residue analysis, led the chemical investigation. Working alongside Marlies Lombard, From the University of Johannesburg and Anders Högberg from Sweden's Linnaeus University, the team selected 10 quartz microliths from the 60,000-year-old layer. All 10 showed macroscopically visible residues, reddish material adhering to their dorsal surfaces. The team employed gas chromatography mass spectrometry, a technique that separates complex mixtures and identifies individual compounds by their molecular signatures. The process begins with extraction. A solvent dissolves whatever organic material remains on the artifact's surface. The resulting solution passes through a heated column, where different compounds travel at different speeds based on their physical properties. As each compound exits, it enters the mass spectrometer, which fragments it into ions and measures their mass-to-charge ratios. The resulting pattern, a chemical fingerprint, can be matched against reference databases containing tens of thousands of known substances. When the data came back, 5 of the 10 arrowheads showed something remarkable. The first samples revealed bufandrine, a toxic alkaloid with a distinctive molecular signature. One sample also contained epibufenicine, a related compound. Both substances belong to a specific chemical family found only in plants of the Amaryllidaceae family, indigenous to southern Africa. The match scores, ratings indicating how closely the detected compounds corresponded to known references, ranged from good to excellent. There was only one plausible source, Buffon distica. Known locally as gift bulb, literally poison bulb, this flowering plant grows across southern Africa's grasslands and rocky slopes. Its massive bulb, which can reach 17 centimeters in diameter, contains some of the most potent neurotoxins in the plant kingdom. The Khoisan peoples of the region have used it for centuries. Traditional hunters still employ it today, coating arrow tips with the milky secretion extracted from the bulb's roots. A small quantity can kill a rodent in 20 to 30 minutes. In humans, exposure causes nausea, respiratory paralysis, accelerated heart rate, and accumulation of fluid in the lungs. The name Buphone itself derives from Greek, bus meaning ox, and phone meaning death. The toxins work by interfering with the nervous system. They don't kill instantly. Instead, they weaken prey over time, disrupting muscle function and coordination. This is precisely what makes them effective for hunting. A small arrow, one that might barely penetrate an animal's hide, becomes far more deadly when carrying poison. The hunter doesn't need to deliver a killing blow. They need only break the skin, introduce the toxin, and follow the wounded animal as it weakens. Over hours, sometimes a full day, the poison does what the arrow alone could not. What this implies about prehistoric cognition is profound. Using poison requires more than identifying a dangerous plant. The hunter must understand delayed causation, that an action taken now will produce effects hours later. They must learn which part of the plant to use, how to extract the active compounds, how to apply them without poisoning themselves. They must anticipate that a wounded animal will behave differently than an uninjured one, and plan their tracking strategy accordingly. They must understand that the poison will spread through the bloodstream, but won't contaminate the meat if the carcass is properly handled. This isn't instinct. This is technology. This is accumulated knowledge passed between generations, refined through experimentation, preserved in cultural memory across millennia. The San people of the Kalahari today hunt springbok, kudu, wildebeest, even zebra and giraffes with arrows tipped in plant-based poisons. The techniques they use bear striking resemblance to what the Umhlatużana evidence suggests: small projectiles designed to deliver toxins rather than inflict massive trauma, persistence hunting that relies on the poison to do what brute force cannot. There is no reason to believe, Lombard has argued, that hunters 60,000 years ago did not do the same. Not everyone is convinced the picture is complete. Some researchers urge caution. The Umhlatużana finding represents a single site, a single sedimentary context, a handful of artifacts. Extraordinary claims require extraordinary evidence, and while the chemical analysis appears robust, independent replication from other locations would strengthen the case considerably. The same alkaloids might have survived elsewhere, waiting to be detected by researchers who now know to look for them. Others raise questions about whether the poison technology at Umhlatuzana represents a continuous tradition or an isolated innovation. Did this knowledge persist through subsequent millennia? Did it spread to other populations? Or was it developed, lost, and reinvented multiple times across human prehistory? The gap between 60,000 years ago and the next confirmed evidence at Kruger Cave, roughly 53,000 years later, leaves room for many possible histories. What remains beyond dispute is what the molecules themselves reveal. The quartz arrowheads from Umhlatuzana rock shelter still carry traces of Bupone distica poison, the same plant, the same compounds, the same method used by traditional hunters into the modern era. The technology existed. The knowledge was real. 60,000 years ago, humans living in what is now South Africa understood something fundamental about the natural world. That certain plants could kill, that this property could be harnessed, that a tiny arrow could bring down prey many times its size if chemistry did what force could not. They didn't know about alkaloids or neurotoxins or molecular mechanisms. They didn't need to. They had something perhaps more remarkable, a system of practical knowledge developed through observation and experimentation, refined across generations, stable enough to leave its signature on stone tools that would sit underground for 60 millennia before anyone thought to look. The poison bulb still grows across southern Africa, its massive blooms rising from the grasslands each year before scattering seeds across the veld. The same plant, the same landscape, the same chemistry. The hunters who learned to use it left their mark on quartz blades that outlasted everything else about their lives. If they understood plant biochemistry well enough to create poison arrows 60,000 years ago, what else did they know that we haven't found?